So hi everybody, I'm Hailey. I'm super excited to be here. I love data visualization. And now my current job, these past few years, I haven't done much, but I'm excited because I'm going to be starting with Google, working on visualizing data for their cloud performance. So I'm a performance guy. My main point in this presentation is like data visualization requires domain expertise. And I see a pattern happening over and over again where companies, especially higher-ups, just assign a generic developer or generic product manager or generic data scientist to look at data and maybe visualize it. And they might not have any domain expertise. They might be good at what they do, a great program manager, a great developer, a great data scientist. But if they don't know the domain that they're doing the analysis for, it can lead to some problems. So this presentation, the bulk of it's on a case from Edward Tufte's second book. How many people have not read the Tufte books? Has everybody read Edward Tufte's books? At least one. The first one's the best, but this is from the second one. But I think what's important to me is explaining things simply, and especially when it comes to visualization, it should be simple. And this is interesting because one of the earlier talks was like this sort of battle between simplicity and complexity. How much do we show and how much do we hide? But if you can't explain it simply, I like what Einstein said, you don't understand it well enough. And Steve Jobs has some stuff to say about this too. So when it comes to designing an interface, what I see, and this happens with when the director says, okay, we need a dashboard for this information. The developer goes and looks at it and says, okay, this looks simple. But as they start looking into it, they realize it's actually complex. So Steve Jobs says, when you start looking at a problem, and it seems really simple, you don't really understand the complexity of the problem. So after I look into it, then I say, oh, it's complex. Okay. Well, it's complex. I'm going to create a complex interface because I have to show all this data. I want to expose everything. I don't want to hide anything. And as Steve Jobs says, then you get into the problem, and you see that it's really complicated, and you come up with these convoluted solutions. That's sort of the middle. That's the part where most people stop, and that's what I see in the industry. But the complex solution is bad, and that's what we're going to see. The beauty is in that simple, powerful, but it's difficult to get that simple, powerful solution. So Steve Jobs says, but the really great person will keep on going and find that the key, the underlying principle of the problem, and come up with an elegant, really beautiful solution that works. So as Steve Jobs says, simple can be harder than complex. You have to work hard to get your thinking clean and make it simple. So my advice is to prototype and iterate as fast as you can. Another problem I see in corporations is they come up with design specs. They maybe spend a couple months in design specs and they implement it without iterating over that interface. So here's a problem. If I want to look at, so I'm a performance guy, so I'm going to be biased towards performance. If I want to design a performance dashboard, how do I do it? I'm looking at a system, I want to decide whether it's working well or not, and if there's a problem, what is that problem? I doubt anybody here knows what this is. Anybody have any idea what this is? This is the standard performance report from an Oracle database. And as far as databases in the industry, Oracle is way beyond everybody else in performance instrumentation. It is the #1 database for figuring out a performance problem. But if I had to deal with this, and I brought these reports into meetings, I've shown the people exact line with their problem, the data, I told them what the solution is for that problem, and eyes just glaze over, and the meeting goes on for the next hour, and people argue. I bring in a nice visualization, maybe a bar chart with a spike, and say, look at that spike. Here's the solution. Everybody's like, yes, let's do it. And so this is an Oracle database, which I think is cool because at least it's shrink-wrapped. This is from Brendan Gregg. These are all the tools you can look at performance issues in a Linux OS. The geek in me loves this. The educator in me, this strikes fear in my heart. Okay, so then I'm going to move on to the example from Edward Tufte. So I don't know if everybody, I don't know what this crowd's like. At my company, some of the people weren't born when this happened. But in 1986, I remember exactly where I was the day after this picture. So this is January 27th, 1986. They want to launch the space shuttle the next day. They've canceled it multiple times. There's enormous pressure to launch it. The engineers who built the solid rocket boosters, the 2 rockets on the sides, they're in Utah. They're going to launch this in Florida. So it's going to be cold. It's going to be colder than any previous flight. So the engineers are frantically faxing data to Florida saying, do not launch. The managers are like, what's the problem? We have to launch. So the estimated launch temperature the next day was 29 degrees Fahrenheit. The problem that the engineers wanted to communicate was, on these solid rocket boosters, there are these cylinders, and the seal between the cylinders is a type of rubber. So as it gets colder, that rubber gets harder, and it doesn't seal as well. And when it doesn't seal, that means a solid rocket propellant can burn through. So what did they do? This went on for hours the day before the flight. So they started faxing information. They sent 13 facts, and here's one of them. Now, if people have a problem with the Oracle performance report, I think they have an even harder problem with this. These three ovals that I've marked, these are three different ways of naming the solid rocket boosters. Now, what is this? When they launch a flight, the solid rocket boosters fall back in the ocean. They go and retrieve the solid rocket boosters and look at them for damage. So they've done this for all the previous flights. So this is damage that they found on the solid rocket boosters from previous flights. Now, they named them in three different naming fashions, which is a problem. They showed tons of information about the damage, but what they want to communicate is not that. They want to communicate that it's the correlation between colder temperatures and damage. But as engineers, and this is the problem I want to talk about a little bit, as engineers, they want to show the exacting information. They show detailed information, which for me is a problem. So here's another fact they sent, and they sent a bunch of misleading information from my point of view, but they want to show the complete picture. They want the managers to understand everything. In the red zone, those were not actual flights. Those were test launches in the Utah desert, so they're horizontal. So the pressures on a horizontal firing of these solid rocket boosters is different from a vertical. So they really should not be sending that information. What they're sending, this is what's called blow-by damage, which is not really what they're interested in either. What they're interested in is called erosion, where it burns through the rubber stoppers. And what's really interesting about this is, okay, did I show us on the next slide? Yeah. So that bottom right, that's the next day's flight. So that hasn't happened yet. Just above it, I circle a 58 and 75. So 58 degrees, it looks like there's damage at the coldest flight they sent, and 75 degrees, the hottest flight. And this causes another major problem. So this looks like there's damage at the hottest flight and damage at the coldest flight. But the engineers were clear. This is their final summary recommendation. The predicted temperature for the next day was 29 to 38 degrees Fahrenheit. On the top right, they say, do not launch unless it's greater than or equal to 53 degrees Fahrenheit. Now, this is where Tufte comes in. So Tufte took the data, the damage data, and graphed it. So this didn't happen that night. This happened later when Tufte did analysis. Now, here's the data, basically visualization of the data they sent. On the bottom is the temperature, and on the y-axis is the number of damage incidents. So the question is, if you saw this as a manager, would you launch the next day? Do you think is there something to worry about? Is there a correlation between temperature and damage? I don't see one. And one of the guys said, and I love this is the classic debate between, I look at management, the techies and the management. Techies are saying, don't do it. Managers are saying, we have to do it. And then somebody says, well, there's damage at the coldest and hottest temperature. What are you guys talking about? So what did they do? They launched. And it was a tragedy. So we can actually see the fire. So that top red circle, that's where it burns through the cylinder into the liquid tank and it exploded. So it was a national tragedy. So what did they do? They launched a congressional investigation. So we go from NASA engineers, like brilliant NASA engineers. Now we're going to go to some of the highest paid lawyers in the country. And what do? They chart it like this. So this is what Tufte calls chart junk. And I've circled in these little purple circles. They mark the damages with different sort of visual effects to show that it's different kinds of damage. And there's no legend to tell you what this damage is. And what they show the temperature. So the goal here is to show correlation between damage and temperature. So they show the temperature, but how the heck do I correlate that? Okay, let's go back and look at what Tufte said. So this is the data that Tufte charted. But let's change it. Let's see if we can communicate our point better. So the first thing that Tufte does is he recharts it, but instead of showing the number of damage incidents, I've changed the y-axis to be the actual extent of the damage. So some of the damages are much more deep than the others. So we're rating now the y-axis on the extent of the damage. Now, this is a huge thing. One of the biggest, probably the biggest flaws is sending the information about the successful flights. There were a lot of flights that had no damage, and the engineers did not send that information. And this is where I get into some arguments with engineers. One of the arguments about this analysis is the temperatures of the solid rocket boosters are unknown. These temperatures are from external weather reports. So this geeky, kernel engineers are like, but you don't know what the temperature of the solid rocket booster is. But from my point of view, this is good enough. It's close enough. And I find this a problem with engineering a lot. They want to be super exacting. But often, getting the super exact information is not possible. But instead of not showing any data at all, let's show data that can be useful. Be accurate enough. So the next thing we're going to do is mark the differences. So on the top right point is now blue. I don't know if that's very visible. It's a different kind of damage. So I don't know if it's important or not, but let's just mark it with a different color. Then let's normalize damage. So at 70 degrees, there were a lot of launches, successful launches, and there are launches with damage. So I average out the damage, success versus damage. That's debatable too. In my opinion, it's a good thing to do. At this point, we have some super cool information. Every flight above 75 degrees didn't have damage. Every flight below 65 degrees did. And now I actually see a pattern. From this point of view, it looks like there is increasing damage. And this is what the engineers wanted to see. But probably the most important piece of information is still missing. This is the known world. Outside of this box, we don't have any data. Where did they want to launch the next day? Where the red X is. Would you have launched now? I seriously doubt it. So the point of this is national engineers failed. So I mean, these like super smart engineers. The congressional investigators, these high-paid lawyers, they made even worse visualizations, in my opinion. So data visualization is difficult, but if we don't do it right, the effects can be devastating. So visualization can be powerful. And believe it or not, in my lifetime, I think this is no longer the case, but when I was at Oracle trying to create a dashboard, the engineers did not want graphics. They're like, I want the exact data. And it took me about 6 months to convince them that graphics were good. So I imagine a lot of you guys, a lot of you know this data. So this is Anscombe's quartet. It's 4 sets of data, X and Y. And the cool thing about it, they're very different sets of data, but if we average it, the averages are the same. The standard deviation is the same. And if I'm going to do a computer analysis, I'll probably do linear regression. The linear regression is the same. So what's going on in these data sets? I know some people are pretty good textual parsers. I'm very weak at textual parsing. But when it comes to graphics, boom, these are the same 4 sets of data. I can see immediately what they're doing. And then the amount of data we can consume, I don't think I need to convince you, but this stuff is amazing. There's over 3,000 counties in the United States. So this is mortality due to cancer by county across the United States. If I had this in a textual format and I was trying to correlate the data, I can't even imagine trying to tackle that. In a visualization, I can immediately see patterns. But visualization can also obfuscate data and be bad. So here's a performance monitor, a famous performance monitor for databases. Actually, it's owned by Dell Computers now. But people love this thing. What it shows is the different components. So the databases are pretty complex. They usually have processes that maintain the database's state. And then you have user processes that get data out, run SQL queries. And then we have a bunch of different caches and stuff. So this is visualizing all the components inside a database. And the idea is you can see what's happening, these things move, and if something goes wrong, they color code it. But this is super misleading. Like something will go red, but we don't actually know the relative importance of it. So like if I read some data off disk and it's slow, I can do 1 read off disk. It could take a second. But my database might be fine. So 1 second's like an eon in computers. And so this thing will flash red. But that might not be a problem at all, because that might have been 1 I/O, and the rest of them are fine, and the average is out to fine. Here's what I call throwing spaghetti at the wall. And this is what I see in the industry right now. Somebody tasks the development team to go make a dashboard. So they go talk to engineering. What should I show? Engineers, here's a list of important statistics. Developers like, OK, I'll show all that in a dashboard. And from my point of view, it's throwing spaghetti at a wall. There's no intelligence in this. Well, there is some, but not much. As a consumer of a product, if I buy a database product or something, I want their performance monitor to have intelligence in it. I want it to guide me, point out the problem, and guide me to a solution. I don't want it to leave me up to figuring it out. It's another database performance monitor. Again, it's throwing spaghetti at the wall. And so I went on to Google, and I said, monitor and charts. And so I was going to look for some bad spaghetti at the wall charts. This is Amazon's CloudWatch. This should be cutting edge. And I'm actually super excited because I'm joining Amazon, and my goal is to redesign this. So imagine you're driving your car down the highway, and this is your dashboard. So this is what, if a DBA from Oracle Database, this is what it's going to look like to them. Normally, it's only run once an hour. Do you want that? Or would you rather something like this? Now, I'm going to have to explain this a little bit. But this takes all the information, all the core information about a performance of a database, and this can be applied to any database or operating system. This is for an Oracle database. But what we have here on top is a load on the database. So the question is, first of all, is there a big load on the database or not? I can see it immediately. Now I see the values going up and down, but is they big? Are they small? What's the relative value? Well, we have something that gives us a relative value. That's the CPUs. So if I'm running on a computer, I only have a certain number of CPUs. And if my load is above the number of CPUs, then I have a problem. So a couple things. This is CPU demand by the sessions running SQL. This is I/O from those sessions too. But CPU, this is how much CPU is available on the machine. That's all I can consume. For example, here I see the demand for CPU going above the number of CPUs. That's CPU starvation. The people that want to run that can't. I can see that immediately. This didn't exist before this interface. You couldn't see that with database statistics. And if I want to fix it, I can say, you know, I want to buy a bigger machine. Well, that usually doesn't happen. Well, what if I'm the DBA and I want to tune it? What I can do, this is a slider window. I can pull over the spike. How do I work on a database? I issue SQL statements. This is the top SQL statements. If I could tune the SQL statement and make it use much less CPU, I wouldn't need to buy a bigger machine. I see all this in seconds, and it's easy. So this is top activity. This is where load's coming from, top SQL, top session. And so the question goes to, so that was just one database. What if I had a real estate of 1,000 databases? What we can do is basically do a tree map. So what this is, so that previous slide is the number of what I call average active sessions. This is like the run queue in Unix. How many processes are active and running? Okay, so how many processes are active and running? This is what that load map shows. So the bigger the territory is, the more active processes there are. And it's color-coded by where they're spending time. So blue would be, I'm spending a lot of time on I/O, green on CPU. And so the databases that aren't very active are off in the bottom right. The ones that really have a lot of activity, I might need to tune on the top left. So this is sort of cool to me. I've been a DBA a lot of my life, and what I hear day in and day out is the database is slow. And I'm just like, it's not slow. But how do I prove it? It's been really difficult to prove. Now if I have this load chart on a database, so the middle chart here, that's the load chart. There's nothing in it. There's no load on this database. The database is not slow because there's no load on it. Now, maybe the developers can't connect to it. I don't know. That's the different issue. But now I know the database is not the problem. So what do you want? Do you want engineering data? And there's nothing really wrong with engineering data in itself. But if I'm trying to communicate information, this could be problematic, like we saw with the NASA case. Same with pretty pictures. I think these obfuscate the data. But if we can come up with clear, simple graphics, then we can communicate our idea very quickly and powerfully. So in summary, textual statistics are difficult in general to parse. Some people are really good at it. They're usually the exception. Pretty pictures are misleading. And the goal is clear, powerful graphics. So graphics can add clarity. But my main point here is it has to be domain expertise. And ideally, somebody who's been in the trenches with whatever you're dealing with, that person has the insights on how to display the data. So basically, that was my talk. So thanks for coming.